We spend so much of our time thinking in two dimensions, right? On a screen, on a piece of paper. But what happens when our problems, well, when they're not flat anymore? Today, we're going to take this leap right off the page and into space itself. We're talking about moving from simple lines to these huge, infinite planes. And trust me, the results are probably not what you're expecting. Okay, so let's start with something super familiar. Think way back to your first geometry class, right? You've got two straight lines on a flat piece of paper. What happens when they meet?
Exactly. As long as they aren't parallel, they cross at one single spot. It's this neat, tidy little point. And in the world of algebra, we have a name for that intersection. We call it a solution. It's simple, it's clean, and honestly, it's totally predictable.
But what if we're not on a flat page anymore? What if instead we've got three vast flat planes? I want you to picture three infinite sheets of glass, just floating and meeting in open space. All of a sudden, that single, predictable point, well, it's not the only game in town anymore.
And that, my friends, brings us right here. Welcome to the third dimension, the key that unlocks this whole new world. It's just a third variable. Yeah, we're not just talking about X and Y anymore. We're bringing Z into the party.
So let's just break down how this whole thing builds step by step. With just one variable, say x equals 5, you've just got a point on a number line. Simple enough. Now you add a y variable, and boom, you get a line. But the moment you introduce that third variable, z, oh man, you don't just get a longer line, you get a completely different kind of object entirely.
Okay, so what does this look like mathematically? Well, it looks like this, an equation with our three variables, x, y, and z. Now, the absolutely crucial thing to get here is that the graph of this equation is not a line. Not at all. It's an entire flat plane that stretches on forever through space. This is probably the biggest mental leap we've got to make today.
Yeah, just let that sink in for a second. The graph of a linear equation with three variables is always a plane, every single time. That is the fundamental rule for everything that's coming next.
All right, so if we have three of these equations, that means we have three of these infinite planes floating around. And this leads us to the big puzzle, the central challenge, the intersection problem. What does it even mean for three planes to have a solution?
And here's the absolute key. A solution isn't just where two planes happen to bump into each other. No, it's the exact spot, or maybe spots, where all three of them intersect at the exact same time. It's got to be a location that is common to every single one of them.
So you know how two lines on a page are pretty straightforward? Well, three planes in space, not so much. The ways they can meet are surprisingly complex. It turns out there are really only three distinct possibilities. You can have one solution, infinite solutions, or none at all.
Okay, let's start with the one that probably makes the most sense right away, a single solution. Just picture the corner of a room. The floor is one plane, right? The two walls meeting there are two other planes. And where do all three of them meet? Yep, right at that one single point in the corner. That's exactly what a single solution looks like in 3D. But what happens if they don't meet at a neat little point? This is where things get really cool. You can actually have an infinite number of solutions. Think about a book. The front cover is a plane, the back cover is a plane, and hey, every page inside is a plane too. But they all intersect along one common line, don't they? The spine. Every single point along that spine is a solution. And then, of course, you can have the final possibility, zero solutions. This can happen in a couple of different ways. First, the planes could just be parallel, like the floors in a skyscraper. They're never going to meet. Or, and this is a really cool visual to get in your head, they might intersect in pairs, kind of forming this triangular prism shape, but there's no single point or line where all three actually meet up. Okay, so let's put the official labels on these scenarios, just to wrap it up. When we get that one single point, the system is called consistent. When they meet along a line and we get infinite solutions, we call it dependent. And when there's no common intersection at all, that system is inconsistent.
All right, let's bring this all home and talk about the geometry of a solution and why it's so important to visualize this.
So why should you care about any of this outside of a math class? Well, because this is where abstract algebra connects to the physical world we actually live in. Solving these equations is literally like finding where different worlds or planes meet.
This kind of thinking is the absolute foundation for solving really complex problems in science, in engineering, and it completely changes how we think about what a solution can even be.
So at the end of the day, solving one of these systems isn't just about crunching numbers on a calculator. It's really about seeing. It's about visualizing how these separate, flat worlds can come together and interact in 3D space. And that leaves us with one final kind of mind-bending thought to chew on. We've seen what happens when three planes meet at a point or a line. But what happens when you add a fourth plane in a fourth dimension? What could that intersection possibly even look like? Now that is something to think about.